Greetings, wonderful college physics students. Captain Rod here, and I'm making this video to help you out with your homework number 1415, numbers 14, 15, and 17 in Unit 1/1 out of your survey text. So let's see, we're going to start with number 14. Now 14 is kind of a conceptual question. There are no numbers. It says something about an athlete in a pool. So let's start with a picture, right? Maybe top view of our pool. And the length of the pool, they're calling it L, so label that. And our swimmer starts here. Let's see, they swim over to here in a length. Now they're calling that time T1. And then they return back to their starting position in a time they're calling T2. Now keep in mind the total time here, I'm going to call that capital T, would be the sum of the two, in case we need that. And this is just an algebraic problem here. So it says for the first half of the trip, what is the average velocity? So you take what we're calling the total displacement here, that's this, I don't want to give it away, but that's this distance here, and you're dividing by the time during the first half, which is T1. Now for the second half of the trip, the displacement is basically the same, but it's in the opposite direction. That has to be taken into account. And just like all the previous problems, the first thing you want to do with this is define a coordinate system. I should have did that first. Let's call this, and then this way we'll call this x equals 0. Right? So the swimmer starts here at x equals 0. They end up here. That would be at x equals plus L in my coordinate system. When they come back to here, they're back to x equals 0. Now keep in mind that when you find the displacement for the second half of the trip, right, delta x over delta t, you have to ask yourself, what is that for the second half of the trip, right? Then you use the delta t for the second half of the trip. Part C, when you do the average velocity for part C, that's for the entire trip. Well, keep in mind the swimmer starts here and they finish here, and that's kind of a conceptual question basically. Part D, now it says to find the average speed. Now speed and velocity are slightly different, right? Speed is the magnitude of your velocity. When you calculate speed, you use distance over time. As opposed to when you calculate velocity, you use a delta x, a change in position over change in time. And these things are slightly different. When this person does this and back again, the change in position and the distance traveled are two completely different things. Make sure you use the total distance for part D. Also for the entire trip, you're using the time, which is the sum of the two. So that should get you by 14. All right, let me clear this and we'll take a look at 15. Get rid of this stuff here. Whoops. We'll go ahead and clear it. Clear all of it. Okay, so 15, something about a cheetah. And the cheetah is accelerating from rest to a V final. Wow, quite an acceleration. 5.3 times 10 to the 7th, or 53 meter. Wait a minute. Jelly like I'll take the right. Cells. Okay, this is not about a cheetah, my apologies. Some sort of cell accelerating at, we're given a time. Let me write this down. Now the delta t I'm given says 700 ns. That ns, the n stands for nano. That means 10 to the minus 9th. So it's a pretty small time. And then we're given an acceleration. So what I'm given here, your numbers will probably be different, is 5.3 times 10 to the 7th meter over second squared. That's quite an acceleration. But again, this is a cell or something extraordinarily tiny. Calculate the maximum speed. All right, calculate the maximum speed here. All right, so although I don't think it says it, but we're going to assume constant acceleration. So let's start with this. Here's our cell. Motion diagram to indicate it's accelerating. Speed is increasing. Define a 0. Call this x equals 0 plus x to the right. Okay, now, and I'm going to go ahead and skip the acceleration graph, but if you assume constant acceleration, that gives you a linear velocity starting at 0. So our velocity against time at t equals 0, we'll assume a velocity of 0. Sometime later, given in the problem, we're going to be at some unknown v final. So the coordinates of this point are a t, which is given in the problem, and a v, which we do not know. And keep in mind that the t is this distance. I'll do this in blue. And the v is this distance. And if we assume constant acceleration, that means linear velocity graph. Now remember, acceleration is delta v over delta t. You have a delta t, calculate your delta v. When it says to calculate the distance, that's the change in position. And remember how you get that. Your delta x is coming from the area bound here, this area right here. Keep in mind, velocity in meter per second times time in seconds gives you meters. So this area here will give you the displacement for that cell. So that should be enough to get you through that one. Let's see here. So that was 15. Now we'll try 17. Okay, it says something about a race car. Let's see, a car reaches a position such that the position fit or the function for it looks like this. Now here's what mine says. It says x equals 4t plus 0.65t cubed. I'm leaving the units out. Where, by the way, these numbers here and here are probably, they could very well be different. Now it says to plot position versus time, and to tell you the truth, okay, they give 4 things here. So 2 of them hopefully you can throw out right away. Hopefully it's obvious this is not a linear graph because of this term right here. This is a cubic type function. So you throw the lines out. The answer is going to be one of the other 2. Now, the way you tell which one, I'm just going to take these graphs here. You got, x against t, and then another one here. And they're very similar in shape. One kind of looks like this, and one kind of looks like this. Well, as far as which one, you can do this kind of by observation here. Look at our function and ask yourself, what is x when t equals 0? And then look at these 2 graphs and ask yourself which one of those matches that. When I'm looking at this, it's reasonably obvious. Okay. So that should tell you which one. Next, where it says determine instantaneous velocities at the following points. Now, let me talk about that one, because that one's a little trickier. Let me get rid of this. And let me redraw those coordinate systems, or those functions. So once you have the graph that you believe in, that you know is correct, I'm going to leave out the detail, but it looks something like this. When it says to find the instantaneous velocity at t equals 3.3 seconds, here's what you do. Give me a moment here. Oh, also notice they're giving you delta t's here, and the first one that's given is 0.4 seconds. So let me talk about what does this crapola mean. All right, so we go to this time on the graph, and you're going right to 3.3 as best you can, and that is here. Now here's the thing about instantaneous velocity. Let me draw this. That's the slope of a tangent line that touches exactly once. So that's the slope of this line. Now here's one way you could have done this. It's not quite according to the directions they wanted, but what we could have done is you draw the tangent line, you find 2 points anywhere on that tangent line, use that to get the slope. That would be a perfectly acceptable way. But here's what they're asking you to do. With this delta t of 0.4, What they're asking you to do is go, hold on, using time intervals of, give me a second here. What they're saying is basically this, that the 0.4, think of it as like this distance on the graph. This distance right here would then be 0.2. So if you come to x equals, let's see, 3.1, and you come up here, and you read that point off the graph, whatever that is. Whoops. Getting used to a new pen. Sorry about that. Let me call that like x1. Then you come over here, and I'm going to add another 0.2 to 3.5, and you come up here, and you read your x2. And notice if I connect this dot and this dot, I'm getting something with really close, almost identically the same slope as this right here. So calculate the slope of the line between these 2 points right here and here, and we're going to use that as our estimate for the instantaneous velocity, or the slope of the tangent line at that point. Now the next part where it says use a delta t, all right, again, I'm getting used to a new pen here, sorry, where it says use a delta t of 0.2. What they mean is 0.2 like from here to here. Actually on this graph it would be like shrinking it from here to here. So they mean this is 0.2. Half of that would be 0.1. So now they're saying you're going to go to 3.2 and 3.4, repeat the process. And then the same thing for the third one. You're just making that delta t smaller. So that should give you a pretty good idea of how to do those. Again, I can talk about it in class if you're still having trouble. So I hope that this has helped out. Have a great day.